I guess I'm sort of restricted to like a half board. So, okay, so the word tameness in this talk means ominimality, not sharp ominimality, just ominimality. And then I'll tell you about multisummable series. Although really more, I'll be talking about the functions that you get from multisummable series.
Well, what is sharp?
Oh, it doesn't matter because I'm not going to talk about it. Yeah. This appeared in Gal's talk on the first day.
Okay.
Yeah. So let's say you have a power series. With radius of convergence r. So now if r is positive, then your series will converge on a disk of radius r, or on the whole plane if r is infinity. And it will define an analytic function in the disk. But if r is 0, if the radius of convergence is 0, then you can't expect to get an analytic function from this series in a whole neighborhood of 0. But using some kind of summation procedure, like Borel-Laplace summation, for example, maybe you can get a function that's analytic, that's holomorphic in some kind of sector neighborhood of 0. So I want to talk about multisummable series, or really, like I say, about the functions that they will sum to. So let me introduce some notation. So in a sector like this, I'll write capital R for the radius. So R is some number greater than 0. And then for this sort of half angle of opening, I'll write phi. So phi is between 0 and pi. And then the sector of radius r and half opening phi is a set of complex numbers whose modulus is less than r and whose the absolute value of the argument is less than phi. And I'm also going to add another parameter.
Does that include 0?
It includes 0. Yeah, I'm doing that. I'll take away 0 when I don't want it. But I'm doing this just to be consistent when I give like a higher dimensional notion of the sectors that I'm going to be working with. But yeah, it includes 0.
Okay, that includes 0. The arg of 0 is just less than everything.
It's you can define it to be 0. Yeah. Yeah, so the argument's valued between negative pi and pi, except define argument of 0 to be 0.
Oh, 0. Oh, okay.
Mm-hmm. Right, so I'm adding also this another parameter k, which goes here. So it scales the arguments here. And now when I write like down here, can you see it? Okay, all right. So let G of R phi k be the set of functions from this R phi k sector to complex numbers that satisfy a couple conditions on the derivatives. So first, the derivative of f over n factorial is bounded by a times b to the n times n factorial to the 1 over k for all natural numbers n and z in the sector. Oh, sorry, sector, yeah. I just said I was going to take away 0 and I already forgot. Okay, so take away 0. So the point is going to be that these functions are not defined at 0. So the second condition is that the limit as n goes to 0 of f and all its derivatives exists. So it's some complex number.
Oh, you mean z goes to 0.
Z goes to 0, sorry, yes, thank you. The limit as z goes to 0 exists. Okay, so this first one, this is like a Gevrey condition. This is a Gevrey condition. An example. So if f of z is the integral from 0 to infinity, e to the minus t over 1 plus zt dt, then this function lies in g of r p1. Sorry that it's a little cramped there. For any positive radius and any angle phi between 0 and pi. And this is not obvious, but you can check that it satisfies the conditions. Now, so if you have a function in this collection, g of r phi k, then it's not defined as 0, but of course you can extend it continuously to 0 because of this second condition, right? So you get a formal notion of like the Taylor series of one of these functions. So if f is in here, we can define a formal Taylor series at 0. So this is some complex power series. And then
Very quick. So the point of the example is, I guess, that when z is on the negative real axis, things blow up. But
Yeah.
as long as you're away from the negative real axis, it's fine.
Mhm. So the power series at 0, the asymptotic expansion you get for this, is the alternating factorial series. Yeah. Okay.
Is every multi-valued function going to be very summable?
Sorry.
Is every multi-valued function here 0 going to be very summable?
No.
No.
Yeah, no. So this setup that I've given you, I'm like starting from a function and then saying that you can get this series because of these conditions that are satisfied. But if you start from the series, like for example from this series, you can take its Borel sum in the positive real direction, and that will give you a function that's defined in a half plane, right? But here I'm saying that you have this function not only in a half plane, but in these larger sectors. And the way that you get that is you can vary the direction of Borel summation in some neighborhood, and that will give you like functions in a family of half planes. And then you can show that on the overlap between these different half planes, the functions agree. And so that gives you this function, not just in a half plane, but in a sector.
Couldn't you say what a Borel sum is like?
Oh, yeah, so it's a summation procedure. So the way that it works is you take the Borel transform of this series, which the important part is you're like dividing the coefficients by n factorial, or the nth coefficient by n factorial. So if the original series has radius of convergence 0, like this one, then maybe the Borel transform will have positive radius of convergence. And then you take the Laplace transform. You show that you can, or if you can extend holomorphically to some neighborhood of the positive real line, then or another direction, you can take the Laplace transform, and that will give you the function. Okay. So
by changing the direction, I mean, multiplying it by phase or something.
you're multiplying it by, or just like rotating you're taking the Laplace transform along a line or a ray, and then you're rotating the ray. So really that just means like you're multiplying the variable by e to the I theta or something. Okay, so
Sorry, going back to the example, can you say what happens when you cross the negative real axis? Like you have a well-defined function everywhere except the negative real axis. What happens when you go across it? Is it like a branch cut or something more?
So in this case, you don't get a branch cut along the negative real axis. You can, if you work instead on the Riemann surface for the logarithm, you can show that you can do this like Borel-Laplace summation in any direction except along the minus real axis. So then on the Riemann surface for the logarithm, that gives you a function that's defined between, so this is the Riemann surface for the logarithm. So this axis is the modulus and this axis is the argument. So you can go from minus 3 pi over 2 to 3 pi over 2. But then of course on the overlap, the function is multi-valued. Does that answer your question?
Yeah, I'm just wondering what kind of a jump happens if you take one value and go across the other. It's like, is it the same jump or is it different as you go? It's fine. You answered fine.
Okay. So this map that takes a function from a sector to its formal series. On this collection of functions. So this map is injective. It's also so it's a differential ring homomorphism, and it's injective if the angle is bigger than pi over 2. And so this comes from a theorem of Watson and Nevelina about recovering a function from its Borel sum, from the Borel sum of its asymptotic expansion.
The K is in the, it's in the n factor. That's kind of tricky because the K adjusts the phi, but also adjusts its constant.
Yes.
The n, but only the one that the n factorial constant, not the a. The a's and b's, they don't.
Yeah, the A's and P's,
Yeah. Is that pretty sharp? Is that one kind of sharp? This fact. We need some.
yeah. So you mean like this bigger?
Yeah,
over
like
2?
phi is equal to pi over 2. It's just wrong. They have counterexample.
Yeah, you can take like e to the minus 1 over z.
Yeah.
And then on the right half plane, like strictly on the right half plane, the asymptotic expansion is just going to be 0.
Yeah.
But then 0 also has like the 0 function also has asymptotic expansion 0.
0, yeah.
So then the map is not injective,
Like e to the minus one over z squared, like that.
probably.
Yeah.
Yeah.
Cool.
Uh-huh.
It's the same thing. Yeah, thanks.
Okay, so, right, so this is like a key fact, right? Because it means that any power series can be associated to a unique function, or at most one function in this class. Okay, so now I'm gonna let G1, one means single variable. So like later on, I'm gonna define multivariable functions. Be the set of all functions from just the unit interval to the real numbers. So now I'm kind of restricting to functions that are real valued on the real numbers, such that, or for which there is a radius, an angle between pi over 2 and pi because of this. Finitely many k's. Oh, I forgot to say, so I'm always going to restrict to this number k is going to be bigger than 1 to just avoid some technical issues. So G1 is the set of all such functions for which you have a radius, an angle, finitely many k's, and functions for each of those k's, such that fi is in G of R phi ki, and it's real valued when you restrict to the real numbers. And this function f is the sum of these f's.
Just on that,
Just on the interval,
just on, okay.
Yeah. On the unit interval. So this function f is just restricted to the unit interval, but it comes from these functions that are defined on sectors.
The sector separate, the R should be bigger than 1?
Yeah, R should be bigger than 1, thank you.
That's strictly bigger than 1.
Yeah, strictly bigger than 1, yes. Okay, so then this fact here extends to this collection G1. So now these functions are real valued. So their asymptotic expansions at 0 will be real power series. And this map is injective. So again, this is important because each asymptotic expansion is associated to at most one function in this collection G1. And G1, like I said, these are single variable functions, and later on I'll tell you about a multivariable generalization of this setup. But now let me
I'm a bit of, can you comment a bit about the importance of the parameter R? Because in some sense, it's not clear to me why you use it.
Oh, you just want, I mean, we just want functions that are defined on some neighborhood, yeah.
It's one, I mean, you have only finitely many things.
In some of the arguments, you need to like slightly shrink R a little bit. So you want to always allow R to be like strictly bigger than 1 and then you might have to shrink it a little bit and some kind of work.
So effectively, 1 plus epsilon.
It's 1 plus epsilon. Yeah, you can always think of it as 1 plus epsilon.
Wait, but if R is big, it does tell you more about the function f, right? Because you have these bounds on a large sector. So I mean, presumably not always you would want it to be 1 plus epsilon. Maybe sometimes it's important to study when R is actually very big and it's bigger, or is it really just 1 plus epsilon?
Right, probably you can like then scale the function a little bit, and that also, lies in this class.
Eventually, she would construct a nominal structure, and really, for any R bigger than a constant, it's already, everything is analytic.
It's already.
Yeah, right. So that's what I'm going to say now. Okay. So, right, so there's this G1, but there is a multivariable analog, which I'll tell you about later, but assume that it exists. So that G, oh, by the way, G is for Gevrey. I don't know.
Can you explain a bit why this is so important to normalize that you are on the reals? 0, 1?
It's not really important.
It's not
Yeah, it's just that you can capture all the functions in this way, right? It's because I'm going to build an ominable structure, and we think of these as like,
Okay.
yeah. So G is going to be the union of these GNs, which I told you exist, but I haven't told you how they're defined yet. And then the result from Dries and Speissegger from about 2000 is that the structure R-alg.
Sorry, what is Gn? You define G1, but
This is what I'm saying. I'll tell you later.
Okay.
Yeah. It's a little delicate. So I'm first stating the result, and then I'll tell you how those are different.
Multisummable and variant. GN stands for.
Well, it's an n variable analog.
Ah.
1 stands for 1 variable. Yeah. So the structure R-alg plus all the functions in this class G forms an ominimal structure. Okay, so these functions G, these are defined on unit boxes, but they don't necessarily they're not analytic at 0. But it includes functions that are analytic, like on a whole neighborhood of the unit box. So it includes Rn, which is a structure we encountered earlier. So the example that drew me to this structure is a function that can be used that is involved in the asymptotic expansion of the gamma function. So the gamma function can be expressed in terms of the exponential function, logarithm, and this function here. I'll call this Stirling's function. It really comes from a series, Stirling series. And this function is what's called one summable for k equals 1 at infinity. But this whole setup I've given is working at 0, so let me switch to working at 0. So the series that the asymptotic expansion that you get is in terms of these Bernoulli numbers. And this function is one summable, which means the k here parameter is 1. And the associated sector that you get, you're allowed to take any positive number r, or any number r greater than 1 in particular, any phi between pi over 2 and pi, right, and then the parameter k is just 1. So the information that this gives you is that you can recover this function from Borel summation in a variety of directions of this series. And what you get is this function on a sector like this. You can take it to be as wide as you want, right? So as wide as you like. And what the theorem tells you is that this function has tame behavior on the interval from 0 to 1. But in particular, it has tame behavior as you go towards 0 on the real axis. Already on any box in this sector, the function is holomorphic. So this function is already, the tameness of this function on any box like this, you already get from being definable in Rn, this smaller O-minimal structure. So what's new in this result is the tameness as you approach 0 along the positive real direction. And so now what I'm going to talk about is that this result can be extended to have tameness in some kind of sectorial neighborhood of 0. Not just for the Stirling series, but for other functions, all the functions in this class. So now let me talk about these multivariable, the GN. So now the setup that I'm going to give now for these multivariable functions is a little bit different than the definition that I gave of the one variable functions. But then I'll tell you that they're equivalent. I won't show you that they're equivalent because that actually is takes some work to show, but I'll give a definition that is equivalent and which generalizes more easily to a multivariable setup. Okay. So in one variable, the functions in G are defined on sectors, or they come from functions that are defined on sectors. But in the higher dimensional case, we don't quite get just products of sectors. It's a little more delicate. There's some kind of generalization, generalized sectors. So let R be a polyradius, so a tuple of positive real numbers. Phi is still just going to be a single angle between 0 and pi. And K is now a tuple of numbers that are either 0 or greater than or equal to 1. And now define a polydisk so this is the set of Z such that the ith coordinate is bounded by Ri. And then this first generalized sector is the set of Z in the polydisk such that K1 times the argument of Z1 up to Kn times the argument of Zn is bounded by phi. So this is a little more delicate, right, than just a product of sectors. The arguments are allowed to interact with each other. And I've added the possibility here for K to be 0, because that works like if K is 0, if Ki is 0, then the argument of Zi is not restricted, right? So that's like taking the rest of the sector with a product with a disk in the ith component. So, okay, we just want to allow that possibility. That's why I'm adding 0 here. And in one variable, this is the same as before. Okay. So now, before, the functions in G were sums of finitely many fi up to fk or fm, where these f's came from, they were associated with different k's. So to generalize that, I'm going to take finite subsets of this. So for a finite subset, the sector associated with this capital K is just the intersection of the s little k's. Okay, and this is the analog of having these finitely many k's from before. So now,
Could I ask a quick question?
Mhm.
So, can you conduct in comparison to Benny's talk on the cell these cells? Can I think of these sectors as sort of hybrid over each other with a relation between, or have you thought about this?
it's a little bit,
Not work.
I don't think that quite works because of the interaction here among the arguments. It can be a little bit delicate.
But it might be similar.
Yeah, it might be similar. Yeah. I actually don't have like a great understanding of the geometry here. I mean, I know they're connected, these S capital Ks, they're definitely connected.
Would be
and
much nicer if one could build it in the same staggered way, but
I should say this, so this setup is all in the paper of this theorem that I just erased of Van den Dries and Speissegger. And they got this setup from work of Tougeron. So this was not, this existed before the O-minimal setup.
So if all your k's are the same, then once the number of variables gets big enough, you're always in the positive real side for all the variables, right? So you kind of lose that factor that the sector goes into the negative real space.
Yeah, but you
If
still,
the k's are different, that's,
yeah, But you preserve the injectivity of this Taylor map though. Yeah, which is really the key point. Okay, so now let me define the functions on these sectors. So, okay, I guess really I think I want to just define the one variable functions again. And then the way that they generalize to higher number of variables is immediate in a way that generalizing the previous definition that I gave is maybe not so obvious. So now I'm thinking again about one variable functions. So R is just a number greater than 1. Phi is an angle between pi over 2 and pi. K is an element, either 0 or something greater than 1. And, oh, sorry, I do still want to take a subset. So K is a subset. Capital K is a subset. Here, finite. And suppose you have a sequence F1, F2, F3, an infinite sequence of functions. And I'm going to index them now by P. So FP will be a function from one of these sectors, almost one of these sectors. So SP is an intersection over the little k's in this finite set of SK R phi.
Now you're in one variable.
Now I'm in one variable, and then I'm going to tell you how this just immediately generalizes to many variables. Union some disk around 0 whose radius depends on P. So the radius is R over P to the 1, P to the 1 over K. P, or maybe, I think maybe this is a typo in my notes. P to the 1 over K plus 1. No, P to the 1 over K. Okay, so it's, sorry, you may have to adjust by 1 here.
Whatever it is.
Whatever it is,
The disk about.
it contains a disk whose radius is shrinking
Even
as
with the
P
intersection.
increases. Yes. So these functions map from these sectors union disks to complex numbers. And I want the sum of their sup norms on the disk to converge. Even if you adjust by some factor here. So this is less than infinity.
They don't have to be continuous. They don't.
They're holomorphic everywhere except possibly at 0. So these functions such that they're defined here.
Everywhere.
To require them to be defined in a disk. Each of them is defined in a disk.
Oh, no, sorry, no, they're not, they're holomorphic everywhere. The sum that they converge to will be holomorphic except possibly at 0. So they're holomorphic, sorry,
On SP.
on SP. Yeah, thank you. So they're holomorphic everywhere. Yeah. So this is the point. You have the sequence of functions P that are defined on this sector, which is not changing, union these disks around 0 that are getting smaller and smaller and smaller. And then because of this condition here, these will uniformly converge on this part, the intersection.
Oh, the FIs in its infinite sequence are these holomorphic things. But
Yes.
The technical sum of them.
I'm going to take the sum of them. Yeah. So the sum converges on this S capital K R phi. Let's say to some function f tilde, and this is holomorphic except possibly at 0. Holomorphic on the sector except possibly at 0.
All right. But one thing I don't understand, the disk is d of r divided by, and I can't really read the x.
Yeah, this is p to the p to the 1 over k.
But 1 over k is the thing that's indexing the functions, it's not finite. There's a capital set, capital K? Which
This
you
is-
said it's finite? You
So
said-
this is an intersection over the elements of this capital set K
Yeah,
of the sector. So these two Ks here are little Ks. Yeah, maybe this is not a,
those are the same.
Yeah. let me change this. So this set can be J.
Oh, so
Okay.
wait, the little k is indexing the functions or it's indexing the,
The little K is fixed from the beginning.
oh, the p is indexing
The P is indexing the functions.
Okay, now I
Yeah,
have. that down.
so let me write
Yeah, no, I got it, that was me, that was really me.
P.
Right.
All right, and now I'm changing this capital K to a J.
Oh, you have the J, you have the K down there. Oh,
So now, was that all the capital Ks? So the little Ks are the elements of this, now this set J. Yeah. And J is fixed from the beginning. These Fs are indexed by P. So the radius of this disk is shrinking as P increases. So you have like, the picture is this sector, if it's particularly simple, looks like some ball union, it's like that. And then this ball is shrinking as P increases. Right, and then because of this, the convergence condition, the sum of the FPs will converge to this function F tilde on this sector here, this generalized sector here. And so the function F tilde is holomorphic except possibly at 0. And now this is the fact that a function F is in the class G1 if and only if you have this whole setup that gives you an F tilde whose restriction to 0, 1 equals F. Okay? And now to generalize this notion of being in this G, this collection G of functions to more variables, it's really just the same. Like I just add bars over some of these things. Again, you have some kind of generalized sector, union a disk, whose radius is decreasing. The same condition on the norms. And then your multivariable function will converge to something that's holomorphic in a generalized sector, except possibly at 0. Okay. So my project with Patrick I was really thinking mainly about the Stirling series, but what we ended up proving is that if you have one of these multivariable functions, which that comes with all this associated information, right? You have a polyradius, an angle, this set J, the sequence of functions defined on these sector union disks that converge to this F tilde. So that means that then there's this F tilde, whose restriction to the unit box is equal to F. And then the result of the theorem is that this F tilde, which is really like a holomorphic continuation of F, is definable in the same O-minimal structure, R alg plus these functions G on not this whole associated sector, but a piece of it. So I should let me write. So this F tilde, this is a function from some Sk R sorry J Sj R P the complex numbers. And you get that it's definable, or it has tame geometric behavior on a smaller sector. So Sj are mu, where mu is an angle now smaller than phi. So you subtract pi over 2, and then you divide by the maximum over the elements of the finite set J, the sum of the tuples. The sum of the entries of these Ks in the finite set J.
The RL plus G is you only added the real valued thing, right?
We only added the real valued
So
ones.
kind of going, because I'm not a logician.
Yeah.
What's kind of going on is you're saying that you can, just by adding the real value things, you can get some, but that happen to be in G, so they come from some guy in G head. You
It-
can define the holomorphic guy
Situation.
G on some kind of smaller, like not this, but
Generalized sector.
sector, whatever
Yeah.
you call the word for that, yeah.
That's exactly the point. Yeah. So just by adding the real valued functions, it's not obvious whether you can define a holomorphic continuation of these things. But the fact is that you can, at least to these smaller sectors.
It can't be obvious because like e to the z is not definable, but the real part as well.
Yeah, so the example that I give when I give this talk to like model theorists or logicians is that there's a structure, if you take R alg plus just the real exponential function,
Yeah,
the real exponential function,
yeah.
then the complex exponential function is not definable when restricted to any open set of the complex numbers there.
Yeah.
So it's really not, you don't automatically, from something about O-minimality, get the definability of holomorphic continuation of a real analytic function.
Oh, I see, that's it.
But just to pursue the analogy with Rn for a moment, right? And Rn, the reason why holomorphic functions are definable is because they're really just real analytic function in more variables. Are the holomorphic continuations of these functions going to be multisummable functions in more variables, or does it just not work?
Yeah, no, it does work like that. You just have to do the computations to show that. Yeah, maybe,
Yeah, for Rn, it's just the holomorphic function is definable just because take the real and the imaginary.
you take the real and imaginary part.
But yeah, for this,
This is a good point. So what I mean by a holomorphic function being definable is that I'm taking the real and imaginary parts as functions of two real variables.
yeah, but for Rn, it is obvious, or kind of obvious.
It's so it's obvious for the functions that are in this collection N,
Yeah.
but it's not obvious for other definable
Like,
functions.
but you
Yeah,
said for Rx, that's not obvious.
for Rx, but it's not even true.
That's not even true, yeah.
Yeah.
That's even less obvious.
Yeah.
So what is the Rn? I lost that.
So if you take like a function that's in like N, this restricted, if it's actually just a restricted analytic function, like a symbol you're adding to your language, then it is obvious. But if you think about what other, and so that's the analog of our theorem. But there are stronger results for Rn that say not just the like primitives in the language, but any definable function has a definable holomorphic continuation. And that's not obvious. Because if you have something on like an unbounded domain, it's not clear that you can like patch together possibly infinitely many holomorphic continuations in a definable way.
But
Uh,
do we know the Alex result for the structure yet or?
No, and that would be hard, I think.
What is it? This, put that out, don't put that.
So-
What's the question?
So this result is about the functions that are in this class G, that they have definable holomorphic continuations.
Yeah.
In Rn, that's clear. This is what Spencer was saying. But something even stronger is true about Rn, which is not that any like restricted analytic function itself has a definable holomorphic continuation, but anything that's definable from these in first order logic
Yeah.
also has a definable holomorphic continuation. So there you can, maybe we can talk later.
Yeah, no, I think that,
And this is not known here. right?
This is not known here, yeah, and I expect that it would be hard to prove.
I think that you can get from the fact that functions are piecewise given by terms. Do you know here that functions are piecewise given by terms?
No.
Is that the issue?
But even in Rn, you know functions are piecewise given by terms, right? And it's not,
In Rn, you can increase the language a little bit, and then they are piecewise given by terms.
if you add a symbol for division. Yeah.
And also for roots.
Roots, yes, right.
Yeah, but
And-
can't you use that to prove what you said, that you can analytically take your function, once it's given by a term, then everything, well, the functions in a term, they have a little bit of continuation.
There's still some work. So this is like a theorem of Tobias Kaiser that you
Okay,
can do this, yeah.
I'm missing something.
Okay, so sorry, I'll try to finish up quickly. So what this means for like the Stirling function. So the sector associated with the Stirling function can be like as close as you want to being a full circle. And so then what this result says is, oh, and the capital J here is just consists of a single element 1 because the Stirling function is particularly simple. So you don't have to worry about dividing by this like sum of these k's here. You're just dividing by 1. So what this result says about the Stirling function is that it's tame, or phi of 1 over z is tame on every sector that's strictly contained in like the right half of this sector, right? And so then this is tame. So switching now from working at 0 to working at infinity, so just involuting this disk, this is tame on something like this, a sector in the right half plane. And now I originally introduced the Stirling function, saying that it can be used in this functional equation for the gamma function. Now it's a fact also due to Speissegger that R alg plus G plus the real exponential function is also O-minimal. Which means that you can use the Stirling's formula to define the gamma function on unbounded domains, which look like, so this picture here, like this. And then the gamma function will have tame geometric behavior on finite unions of these strips like this. Union, you can also finite compact boxes. So the gamma function has tame geometric behavior on finite unions of strips like this. And then one last comment I wanted to make. Is that in general, this theorem can't be improved, meaning you can't get tameness on, in general, wider sectors. And again, an example to show that is the Stirling function. So along any line like this, if you look at phi of 1 over z plus phi of 1 over minus z, then this function will witness infinitely much oscillation along this line, like as you approach 0, from either direction, it doesn't matter. So what that means is that you can't extend the tameness to some like sector of wider opening, at least one that's symmetric around the real axis. Because this sort of infinite oscillation violates O-minimality.
But when even for the gamma, even for the gamma function can't be defined on like that line. Really, just the gamma function, I guess, is defined in terms of Stirling function, but it's not. Or maybe is it like clear that the fact that the Stirling function is not definable implies that the gamma function is not.
Oh yeah, good question. So like if
Bond.
you could sort of extend these strips and they kind of go like that.
Yeah.
So this is not obvious that it's, so if you just look at one single strip, this could be definable in some O-minimal structure. There's no reason I know that means that you somehow witness oscillation here from the gamma function. But it won't be definable in this O-minimal structure.
Yeah, okay. But do you know that the restriction of gamma to the imaginary axis
That is
not definable?
That's definitely not definable because all these strips here correspond to fundamental domains of the exponential function. So as you go up, you intersect infinitely many of these fundamental domains. So you oscillate around and around.
The strip just like pulling back bound in imaginary strips under the.
Exactly. Yeah. Mhm.
Gamma. Oh, but can you get it from the gamma z? There's some formula like about sine z. A little bit.
Okay. Yeah. So we have actually a similar result
Yeah.
for a different O-minimal structure in which the zeta function is definable.
Yeah.
There is an O-minimal structure that amalgamates this one, this RG, and this other O-minimal structure where zeta is definable. We didn't work through the details for that amalgamation, but I would imagine that they would probably work. But then the functional equation that involves, gamma and sine and zeta, the regions where those are definable have finite or have bounded intersection. So there's no hope that you could like get the
is that part of the motivate why you like the gamma function, the zeta function, like
I think the gamma function is also just it appears a lot in math. It's more than just with the holomorphic.
For the structure, the zeta is a generalized
Convergent generalized power
I don't
series.
think you can extend to any sector, right? Because
You can't extend to any sector.
So I think that's what you mean about this would work for the amalgamated one. Because if you amalgamate, it really has to be only on the real line, right?
Yes, but I think that maybe there's some kind of like you could have the zeta function on a strip.
You mean
And the-
on like sectors
And this on strip,
generalized
yeah.
vectors on
Yes. Right. But the last thing I wanted to say is the infinitary oscillation that you get from this function looking on this line is something specific about the power series, the asymptotic expansion of the Stirling function. Specifically, it's that the asymptotic expansion is odd. And also it's something about the properties of the Borel sum. You can do some kind of computation. So what the point is that this oscillation you get if you would try to extend the tameness to some like wider sector is not something general about multisummable functions or functions that come from multisummable series. It's something specific about the Stirling function. So if you have like a series, a multisummable series, and you look at the function that you get through summability, then it could be tame in a wider region. Our result does not say it's not tame in a wider region in general.
So are you saying that because you look at this asymptotic expansion
Mhm.
and okay, somehow it cancels out to have, let's say, only positive coefficients, and then it can't come from a quasi-analytic class? What's going on here?
No. It's so the reason why these two functions are related, the like 1 over z and 1 over minus z, that comes from the oddness of the series.
Yeah, but so because it's odd, when you sum, some things will cancel out. But just I know that if you have a series with only positive coefficients, for instance,
Yeah, then
it cannot be algebraic,
right.
right? So is this is the kind of obstruction that you get here, or it's something
Mm.
different?
It's something even more specific than that. It's like the oddness of the series says that you have a relationship between these two, and then an additional calculation shows that this equals something oscillatory. Yeah, so it's really like highly specific to the Stirling series.
Yeah, but I wonder if you could get like a general argument where, whenever you somehow build something and it has positive coefficients, and then you just know it couldn't be in your algebraic class just because it's
Yeah, well, that would be true, right? I mean,
okay, but it wouldn't say that it's not O minimal in some others. You're saying it
Yeah.
turns
this
out
one
to
is
be some-
not O minimal along like this line in any O minimal. It's not definable in any structure. I'm finished. This is all.
Question. So, very stupid question maybe, but if you had asked me to prove something like this by only knowing the previous result, I would have thought, well, I know that if I take the Borel sum along some line and I have tameness along the same line that bisects the half plane where the philosophical goes. And here I can say, well, I know that the poles in the Borel plane for the Stirling series are on the imaginary axis. So I am free to rotate all the way up to pi over 2. So somehow I should have tameness all the way up to pi over 2.
That's the intuition. Yeah.
Okay, but it's not
But-
so simple. This is not an argument.
It's not so simple because what actually goes into this structure are the restrictions of these functions to the real numbers, right? So the functions in here are like real functions. They're functions of real numbers. So you should have tameness, like as you do, you like rotate, right? But then to actually show that it's definable here, you need to like do some computations. And that's, I mean, the proof is essentially some computations.
Okay, and
But
also
I-
you need to know that it's like I mean, you can show this for every angle, but you need to know that you can do it uniformly for all the angles, so that like,
That's a
gives
good
you
point.
one-
Yes.
gives you one
Yeah.
like function in 2 dimensions.
Mhm. Yeah.
Yeah, a small question. What kind of issues do you run into when you allow K to be like 1/2 or?
Oh, so we don't deal with those issues actually in our paper, or those issues don't arise in our paper because we work on the Riemann surface of the logarithm. And so the restriction of not allowing K to be between 0 and 1 comes from working in the complex plane. But as soon as you move to the Riemann surface of the logarithm, you don't need to worry about that.
Do you know anything about just the positive imaginary axis? If you restrict gamma to the positive imaginary axis?
Yeah, that's not definable in any O minimal structure.
It's also not.
Yeah. The gamma, you said gamma, right?
For gamma.
For gamma, it's definitely not definable, but the oscillation comes from like the exponential function in this.
Ah,
Yeah.
oh, sorry, but I meant after removing this
Like log gamma, for example.
I mean,
or the Stirling
just the
function.
Stirling one. I mean, or without the log. Yeah,
This
the
is
Stirling
something,
log.
so Patrick told me, my collaborator Patrick told me that he was thinking with the student about whether there's a new O-minimal structure where you get definability, along the positive imaginary axis. But then he said that actually this seems more complicated than he initially thought. So I don't know. You can
I
ask.
Patrick
Yeah.
about this as well. And, I was
Okay.
Patrick if you had.
No, I haven't thought about this. Yeah.
A bit, because there's a paper of Thomas and some of his collaborators here where they do some rotated Bessel function. It's kind of similar for the Bessel function. It's also summable up to the imaginary axis. It stops being summable on the imaginary axis. But on the imaginary axis, it's Pfaffian for some reason. So actually the restriction to the imaginary axis is in some other dimensional structure that I just.
But okay, for the Bessel function, you start with a differential equation, right? That's
Yeah.
not the case here.
No, definitely. I don't see why this would be fine, but just it happens there, but it stops being Gevrey.
Oh, but it is definable for another reason.
It's
Okay.
definable on the imaginary axis.
Yeah.
And I also don't know some stupid reason why it shouldn't be definable.
Yeah, this argument only works if you're not this line. So any other line in the sector, you get oscillation, but not here. So it is possible, yeah, that it's. Mhm.